Okay, hang on. So lab 33, right?
Yeah.
Okay. I'm actually having trouble getting Jupyter to work on this machine. Every time I launch the lab, it wants to run the server, and I don't know what that's about. I've been trying to troubleshoot it for a bit, and I can't figure it out. But I can still run through the lab. And I do have it open now. So let me get that.
Okay, I'm going to hand off control to you then.
Okay.
You are now the host.
Only thing I'm going to do now is should be a blur option.
And your screen and video is not sharing yet.
Oh, well, I suppose it doesn't matter. Everybody can just look at the background of my room. Okay, let's see. Okay. So everyone will have to excuse me. I'm not on my normal setup. I do have the chat open. Hopefully people can hear me and see my screen. So we can continue. All right, so for this section, I got about half the grading done. I got a long drive, and then I'll do the rest tonight. So most of you should have about half of your labs in the last week or two done. Let's see, there's some in the grading room still. Okay. So today we're going to be talking about KNN classification. So what's KNN? Well, it is the K nearest neighbors. So K is some number. Could be 1, could be 2. So it's talking about pick a number, your 2 nearest neighbors, your 1 nearest neighbor, your 3 nearest neighbors. That's what it's all about. So if you recall, we talked about classification last time. And the difference between regression and classification being we, instead of wanting to have a line that lets us predict forward and backwards, with classification, we're wanting to classify data into however many segments we want. So far, we've only done 2. But now we're going to be talking about what could be more. So here's an example. We have the species of plant of the iris, and there are different subspecies, breeds, I guess, and we want to be able to classify them based on the lengths of the petals and the sepals, if that's how you pronounce them. So this is a well-known problem, and it's used a lot in pattern recognition training literature. It is what you're given is a data set that contains information on the sepal length, width, petal length, width, all in centimeters, and class of iris spleens. The data set contains 3 classes, 50 instances each, where each class refers to a type of the iris spleens. Hence, it's a multi-class problem, and the number of observations for each class is balanced. So you can see, I don't know if I can actually zoom here. There are, if you just look visually at the pictures here, even though you might be inclined to say these are the same kind of flower, you can definitely tell that there are some different subclasses. And the way we are going to put some numbers to that and actually use them to classify them is we're going to look at the length and width of, there's two different parts of each of these flowers. There's the petal and the sepal. Again, you'll have to excuse my pronunciation. So let us use a k-nearest neighbor model in Python. So, and see what we can do. All right, so the libraries we're going to need, pretty standard. We're just going to read in our data set, and gee, I wonder what we're going to, what kind of thing we're going to put this in. Could it be a data frame? Yes, it could be a data frame. So the columns we're going to want are what we were just talking about. If you remember back to the binary classification example, we had a whole lot of predictors, and then we had the outcome. These are our predictor columns, and the class is going to be the one that we're interested in predicting. This is the result. I think that was the one in the credit card example. It was called result. I'd have to think back. So we're going to name our columns the sepal length, the sepal width, the petal length, and the petal width. And then we're going to read in our data set, and the data set is found here. We're using the get and URL requests. So let's look at some of the data to make sure it's something and exists and isn't garbage. And here we have it. So what does a piece of data look like? Well, everything's in centimeters. That's and they're all in numbers, so that's good. That means the data is kind of what we were expecting based on what our problem description was. And we have the actual classification for whatever flower this was measured from. So someone took flower, measured the sepal length, sepal width, measured the petal length, petal width, and then them knowing what class it was, actually wrote down what the class was. Now you may notice that the all of these are the iris virginica. If we were to change this to randomize the order of these, or if you just simply sort by length, we would get something different because the data is sorted by class. I remember from last time. Additionally, we can describe some of these things. Notice that, again, we don't have anything for class in the describe. That's because it is non-numerical. What do we get usefully? What are some useful things we get from describe in this case? Well, again, this is one of those cases where we're more interested in the fact that it is numeric data rather than the actual numbers here. What would be interesting is if we were to split this up into 3, so take all the virginica and then do the describe, because then we would be able to look at the differences in the mean and the standard deviation and whatnot between the 3 different classes. That would be kind of interesting, but at least we know that the 4 columns, 4 numerical columns, are valid. Okay, so what we're wanting to do now is we want to get the predictors, which is the 4 columns I mentioned, and the target, the outcome. So we want to get the predictors. We want everything in the vertical direction. And we want to go from the beginning to all the way to the end, -1. So we want everything except the very last column. So this will be our predictors, our X, our independent values. And our dependent values is going to be everything in the vertical direction, and then just the last one. So there's 5 columns. We could have just said, you know, go all the way to second to last, but this works just fine. In fact, this works in all cases, so it's more general. We're going to use an 80-20 split to chunk up our data. We're going to use part of it for training, if you remember last time, and part of it for testing. So can someone tell me the difference between our training data and our testing data? What do we do with each, other than the obvious? What do we use our training data for, and what do we use our testing data for? We reverse it? I'm not sure what you mean by that. Yes, that's exactly correct, Jackson. So the training data, the training data and the testing data are kind of the same in the sense that they all come from the same data set. If I shuffle the data set, you could get different specific training data and different specific testing data, even though you're still using the same split, 80-20. The point of this is we're going to take our data and we're going to say, all right, cut out 80% of it. We're going to train our program, train our machine using that data. What does it mean to train? Well, I'm going to say, okay, machine, here's your first entry. You've got something of length 5.9, 3.0, 5.1, and 1.8. That's the measurements. And the classification is Virginica. It goes, okay. But that's not enough for it to be good at predicting stuff. So I'm going to feed it some more data. I'm going to say, here's another thing to train with. And then it's going to be like, okay, I'm starting to see a pattern here. I'm going to feed it more and more and more and more and more and more. So I'm going to do that. I'm going to repeat that until I've used 80% of my data so that the machine has a decent pattern to work with. But we're not done yet. In order to see if that pattern is any good, we're going to use the remaining 20% of the data. And we're going to chop off the classification. We're going to feed it the predictors, and we're going to see what the machine does with its pattern. It's going to say, okay, well, you fed me these 4 numbers, and based on what you've told me before, I'm going to say it's Iris Virginica. And then we're going to compare what the machine predicts versus what the actual measured data was, and that's the testing data. So that's what we're going to do. We're going to split it up. And luckily, we don't have to do any funky, weird things to do it, to manually do it, where we have the method from Sklearn to do it ourselves. So we're going to use our train test split method. Is it a method? I don't know. We use our train test split function from the train test split package. And what is it going to give back? It's going to give 4 sets of data, or X training, or X test, or Y training, or Y test. And we're splitting it up in 80-20. So if the decimal you put here is going to show you how much testing data you have. So if we had 150 records, that means we're going to have 120 to test with, or train with, sorry, and 30 to test with. Okay. So it's pretty straightforward to train the K nearest neighbor algorithm, especially with the Sklearn package we have. The first step is we want to import the, so see how we imported the train test split part? We're gonna do the same thing with K nearest neighbors. And in our second line here, it's going to be given 1 parameter. And remember how I said before, this is K nearest neighbors, where K can be a number. Now we're telling it what that number is going to be. Now, it might seem a little weird that we have N neighbors here rather than K. It's because, well, 2 things. Generally, when you're asking how many things should my function have, N is a good number to go, or a good letter to go to. It's the first kind of thing that pops up. N or I are usually the, you got I, J, K, you got N, M, whatever. So we use the number K, or I keep saying that. We use the letter K. Otherwise, this would just be N, N, N. It's kind of, it would be N nearest neighbors. So that's one reason it's K. The other is that it lets us distinguish between there is the world, the problem of K nearest neighbors, and then there's the actual N you plug in. So what's the N we're plugging in with? 5. We're saying that we want to do a K nearest neighbors kind of classification using 5 neighbors. So there's no ideal value for K, and we're going to be selecting it after we do some testing and evaluation. Let's start out with 5. It also happens to be the most commonly used value for our algorithm. Okay, So we've selected a value for the number of neighbors we're interested in dealing with. And let me take a moment to try to explain that a little better. Usually, at least in computer science, when we talk about k-nearest neighbors, it's in relation to distance in like a map, like a geographical map. So pretend for a moment we have a map with cities, and we also have a relation between cities about the distance between them. Now, this distance could be total distance, like from here to here, or it could be there's not always a road from every city to every city, so the distance from this part to this part is this distance plus this distance. So could be any of those. So assume there's roads all over the place. So question is, what are my two nearest neighbors to this city right here? Well, I don't know. Granted, I didn't draw all the roads yet, but even assuming I didn't, well, we're going to calculate the distance between every neighbor, or every thing on our map. We don't have to calculate them all, but we can. And then we're going to sort by the distance but from here. And we're going to say, yeah, pick the two that have the shortest distance. Okay, it's going to be, let's say, this one and this one. So those are our two nearest neighbors to this. So we could, if we wanted to, classify this as, I don't know, a selection of cities, classify this as a selection of cities, and this is the two nearest neighbors to each. That's generally the problem setting we talk about when we're in a programming class, at least in my experience. This one is completely fine because instead of measuring distance, we're talking about the classification of, is this particular flower closer to a classification 1, 2, or 3? Virginica, Setosa, and Versicolor. Okay, so that's what we're trying to do. And we've split up our data and we're ready to do that. Okay, now we do the fit method. And the final step is to make predictions with our test data. So we've used our training data. We've told our classifier, okay, I don't want you to do binary classification. You're going to do classifying with 5 as your parameter. Here's the data I want you to train with. And now I want you to predict using the test data. Now, what is this going to do? It's going to give us, so remember, we had our 4 input columns, and we had our 5th classification column. So I've trained it on everything, and we have the actual output, not the output, the actual data measured. It's the green line. And now I have this predicted output from my model I trained. And so we're going to see, is the column I came up with, the blue column, close to the actual output, the actual measured data, the green column. We'll see how close they are and see if we have any false positives, false negatives. It's kind of hard to say false positive, false negative in k nearest neighbor because that would imply a binary, but it's still, that would be analogous to how many times did I predict class 1 when it wasn't class 1? And how many times did I predict class 2 or 3 when it was class 1? So errors is what we're looking at. So again, we're going to have a confusion matrix. And what we had before in our binary classification example, wish I had my welcome tab with me. Remember, we had the 2x2 grid because, as I said, it's binary. You've got false negative, false positive, true positive, and false and true negative. So there is, we predicted correctly the positive, we predicted correctly a negative, we predicted incorrectly and we predicted incorrectly for this one. Well, in this case, we don't have true or false. We have class 1, class 2, class 3. So instead of a 2 by 2 being 4 total outputs, we're going to have a 3 by 3. Now, what are the possible scenarios here? It's really not that different. It's kind of what I was talking about above. We've got, all right, class 1, a correct prediction. We got a prediction of class 1 when it was actually class 2. And we have a prediction of class 1 when it was actually class 3. We have a prediction of class 2 when it was actually class 0. We've got a correct class 2 prediction. We have a class 2 prediction when it was actually class 3. We have a class 3 prediction when it was actually class 1. Class 3 prediction was actually class 2. And a class 3 correct prediction. So you can kind of view this as, let me see what the best color here. We have correct predictions for class 1, 2, and 3. We have incorrect predictions of class 1, incorrect predictions of class 2, and incorrect predictions of class 3. So what were our actual numbers in that? Well, let's look at the picture. Notice that the K being 5 doesn't turn this into a 5 by 5. The K being 5 simply says, how many things do you look at to infer what you are? If I say only look at 1, that means I'm only comparing the properties of the thing I'm trying to predict to only the very closest thing we're looking at. So according to this, we correctly predicted 1, class 1 pretty well. We didn't have any errors actually. In class 2, we had 1 prediction of class 2 where it was not a class 2. And then for class 3, we also didn't have any errors there. Well, what if we had a different value for K? What if we use something other than 5? What's the best value for K? Well, there's no direct answer for this. It's one of the things that you need to refine and figure out. There is a best value for K for each situation, but there's no general, you can't know it beforehand. One of the ways to help find the best value to K is to plot the graph of the K value and the corresponding error rate. So what's the error rate that we have going on here? Well, if you remember, we had the measurements of precision, accuracy, and we also had the R value. Well, if we change the value for K, 1 through however many we want to go, 50, let's plot what the error looks like as we move along. So we're going to make a list, call it error, and then we're going to iterate 1 through 50. Do the same thing we did up here. We're going to set our neighbors to whatever our I value is. So I'm going to start out 1. All right, make our neighbors 1. Do the fit, do the prediction, and add the mean of when the prediction is not what the test data is. So remember earlier when I had the blue column and the green column? Compare the blue column, which is the predictions, to the green column, which is the actual measured data. Count up all the times it's a mismatch. So in our case here, we had 1 mismatch. Get the average, the mean, and put that in our list of errors for 5. That was 5 neighbors. And so the position in our list here for position 5 is going to be 1. We had 1 mismatch. Do the same thing for everything else, 1 through 50. And then what we're going to do is say, all right, look through I did the process of training, fitting, selecting the number of neighbors, and then I counted the mismatch. The number of mismatches is the metric by which we're going to figure out what the best number of neighbors to run with is. All right, let's do that. And now we're going to plot it. And here's what we get. So from going from 1 to 50 as the number of neighbors I want to look at, this is the average error we get. And why do I say average? That's kind of weird. I have my data here, right? I've got my training data. I've got my test data. Well, if I choose 5 as my K, won't this be the same every time? Why do I need to use the average instead of I just know it? So the question is, for a given number for K, so let's say 5, why do I need to have the, yes, that's exactly right, Catherine. Because when we split up the data, we tell the machine, split up the data, it's going to do it randomly. So all we know is it's going to be an 80-20 split. We don't know, and it's a good thing we don't know. It's a good thing it's random, because if it were the same thing every time, it would be like, I want to know something about this deck of cards, but it's sorted spades first. And I'm splitting it 50-50. So I'm going to get all the spades and all the clubs. It's like, okay, the entire deck's spades and clubs. That's it. I got the first half of the deck and I'm predicting with it. It's nothing but spades and clubs. I should assume the rest of the deck is spades and clubs because it's what I've been handed. But no, it's actually shuffled. We shuffle the data for 5 neighbors. And if I do 5 neighbors again, I'm going to shuffle the data. So yeah, that's why it's the average, the mean. So look, the average error, I keep saying average, it's the mean. The mean error for 1 through 4 appears to be 0.07. And that's the error rate. It's not the actual number. It's out of 150, how many errors were there? And we kind of have a plot going on here. So let's poll the audience. What seems to be the best value for K? Should we choose the smallest number here or the largest number here? Largest. I assume from the caps, from the all caps, that was a joke. It's a good one. But let's run with that for a moment. Let's say we wanted to maximize our error rate. Okay. Well, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 values that would give me the largest error rate. So how do I know which one's the best? Which one should I pick? If I have 8 values for K that all have the same error rate, which one should I go with? It's a great question. Does it matter? The answer is no, it doesn't. If you're trying to choose a value for something like this, what's the best value to choose for the number of neighbors? If they're all the same, if they all have the same rate, then it doesn't matter which one you pick. You can pick in any method you choose. You can randomly pick. But if they're all the same, I may as well just take the first one. So we would take 33 or whatever this is. But no, we don't actually want to maximize our error rate. We want to minimize our error rate. So we want the error rate that has the lowest average. And what is that? Looks like 6. So it looks like if we look at our 6 nearest neighbors, it gives us the smallest amount of error in our classification prediction. Okay. So a brief summary of what we're talking about here. Instead of a binary classification where we're saying something is either, let's say, true or false, diabetes or not diabetes, fraud or not fraud, we have a situation where we want to classify things into a number of groups. We don't know how many. Additionally, when I have a item I want to classify, like this one here, in order to classify where it goes, I want to look at a number of neighbors to figure out what I want, what I want, which bucket I want to throw it in. Does this go in bucket 1, 2, or 3? I don't know. I've determined that looking at my 6 closest things and looking at their classification is the best way to do it. Okay, so I have a number of classifications. I'll call them buckets. Bucket 1, bucket 2, bucket 3. I also have a number of flowers that I want to look at that are close to my current sample that'll tell me which bucket to put it in, all right? And then what I want to do is get the parts of my data that are predictors, the parts of my data that's the classification, chunk it up into some amount for training and testing, choose the best number for neighbors, do the training, do my prediction, and now I can say whether or not my classifier is any good. Now that we have a classifier, I can feed in whichever flower I want. Now, as I mentioned, the machine I have access to, how many miles away am I? 400 miles away from home. I couldn't get Anaconda to actually run it. I don't think I have permission. So I can't actually run these cells here. However, I'll tell you what we would need to do to run them. And additionally, I should be home by 5 o'clock. So that recording will have this part actually in it. So we've actually trained a classifier. Now, there's something about this classifier that's not optimal. There's something I would like to go back and change. Does anybody have an idea of what I might want to change in this classifier? So here is how we built the classifier. We got some data. We turned it into a data set or a data frame. We trained it with 80-20. We chose 5 as the number of neighbors. And then we actually did the training. Yes, Hunter, that's exactly right. Later on, after we actually trained it, we said, maybe the number of neighbors isn't the best as 5. And we decided that 6 is best. So we would change the number of neighbors here to 6. Okay, so change that to 6, run it all again. And now we have the database that we want. So now we actually want to predict what the outcome of this particular, and you can all probably do this at home, so tell me, I'd be interested to see, this particular flower. This is the data we have for a flower on the numbers. And our classifier will tell us what the classification, Setosa, versicolor, or virginica, that this number will be. So I would say, is there any lack of clarity in how you would do that? Because unfortunately, I can't actually do it for you right now. What are we supposed to do after changing K? Nothing really, you just rerun everything. So the way our classifier worked, we made our data frame. That doesn't need to change. We looked at some stuff in our data frame. Nothing needs to change. We described our data frame, nothing needs to change. This doesn't need to change. Here's the first change we make. After that, since this is all in the same cell, you don't really need to do anything else, but we need to fit it again because we chose a different number of neighbors. We need to predict again. This will get us a new confusion matrix. And after that, we don't need to run any of these because this was telling us what the best number for K would be. So simply all you would need to do is we have our classifier, and what it does is it predicts the outcome. I might be able to, I can put it up here. So if I were writing a new cell, the way Y predict works from my classifier, whatever I feed this is the length I'm going to get back for Y predict. So if I feed it a list of stuff, so here's 1 flower, 2 flower, 3 flower, oops, 1 flower, 2 flower, 3 flower. Oh, I suppose I could have just done text. That would probably be better. So this would give me back, you know, class A, class B. But if I feed it one thing, if I feed this one thing, so just one piece of data, so let's say flower X, what it's going to give me is a class A, a class B, or a class C. So all I need to do is, in this case, we have our, 6.9, 3.1, 5.1, and 2.3. That is the flower we're feeding. And what Y predict would be, it would be the list of stuff that our test data was. And what's our test data? It's 1 flower. So it would be a list containing the classification for that 1 flower. And I don't remember off the top of my head what it was from last semester, but that is all the exercise is. It is a, you've done, get rid of that. I suppose I can leave it up unless someone thinks it's distracting. We took our data, right? Doesn't Y predict need to be X test to compare it to the other? We already compared it to the other data, right here. Yeah, it's a different variable. It doesn't really matter so much if it is or isn't a different variable, because we predicted with our test data, and then we printed out our confusion matrix for that particular test data. And we said, okay, it's good. Now I want to use some different test data. I can either add it to my old test data if I want, but then I would probably lose it, as in I wouldn't know where it was. Or I can make my test data this one individual flower. And we're not going to be generating a new confusion matrix. All we're wanting to know is, what does the classifier predict this to be? So after I'm done with all that, after I've actually tested it, I would just tell me, so Y predict. Or if I wanted to, I would just not even say, save it to a variable. I would just say classifier. So classifier, I want you to predict something. Predict for me, classifier dot predict. Predict me a flower. Okay, what's the flower? No, it's 6.9. 1, 5.1, 2.3. Predict me for this, and I just hit go. And because I didn't save it into a variable, it would just give me a value. And I don't know off the top of my head what it would be. Should be a list containing only one item. I don't know the legality of letting you share your screen on a recorded. Lab. If it's saying, so Catherine, does the error say it's expecting a 2D array? Interesting. Try putting a second set of brackets around it, like this. So the difference between 2D and 1D is every time I add a collection of, or a set of brackets, I'm changing the number of things. So if I don't have any brackets at all, I just have a number, 0. If I have one bracket set, I'm saying I have a collection of numbers. If I have 2 brackets, I'm saying I've got a collection of numbers. And that's kind of what we have here. Our flowers are a collection of numbers. It's 4 numbers. So we have a collection of flowers, meaning I have a collection of 4 numbers. 4 numbers here, 4 numbers here, 4 numbers here. So I'm just curious, what did it, so it worked, what did it say it was? Virginica. Cool. All right, well, I'm sorry for the having to do that by proxy, but funerals are a thing. So does anybody have any questions, comments, concerns? Poems? I wouldn't know what the Sklern error is about. It's possible that, oh, did you change? I think I know what it would be. You would not want to change it here. So undo all the changes you did. Copy this. Well, that's not entirely true. Undo all the changes except for this. Change. This needs to be 6. You want to put that line right here. You want to do the training. You want to do the prediction again. This is a different prediction. Let's put it at the bottom of the page. But did you get Virginica also? I think that's how you pronounce that. Catherine, did your prediction come out as Virginica? It's possible that it wouldn't, because you both have random splits of the data, but I would generally think that not. Either if you saved it as a variable, so just say after you did it, y_predict, like this, and then rerun it, or don't save it as variable. I have the chat box, don't I? So if I say y_predict equals stuff, either say y_predict in the new cell below, or get rid of it and just do whatever the stuff was. So everything, delete the y_predict and the equal sign. Get rid of that. It doesn't particularly matter. Yeah, Virginica, cool. It doesn't particularly matter. I was just curious. Okay, so that was as good a job as I could do. Hopefully, it wasn't too confusing. It's very similar to binary classification. It's just that instead of, you want to look at a certain number of neighbors to figure out what you are. All right, then. I do believe we've had enough time for questions. So I'm going to end it and get back to section 1 grading. Yep, no problem. Office hours tomorrow as usual. And if you have any questions, feel free to email me. Thanks.